Thank you, Brian. Good morning, everyone. I hope you're having a great conference so far. My name is Ravi. I work in the non-volatile memory solutions group at Intel. I specifically work in the Optane team. I hope you all have heard about Optane. It's the latest and greatest SSD technology. In a brief while, I'm going to be touching briefly upon what Optane is and what Intel memory drive technology is, because Optane is the underlying hardware that is leveraged by the software called Intel memory drive technology. I have my email and Twitter handle on the screen here. Please feel free to connect with me on those platforms. So let me start with the problem statement. What is it that I set out to achieve from this exercise, right? I wanted to optimize the performance of Apache Spark and get more out of my infrastructure while operating within the budget. Now, pay attention to that. The key statement here is I wanted to be operating within the budget, right? And because if I want to optimize Spark throughput, there are standard ways of doing it. One is you can optimize the software configuration, right? Change some variables in your infrastructure, Spark configuration, et cetera, to get more out of your Spark performance, right? Or you can actually buy more hardware, whatever infrastructure you have, expand on it, get more hardware of the same nature, right? But that's just standard way of getting more out of your Spark infrastructure, get more out of your Spark performance. But if it's just about standard way, I wouldn't be here talking about it, right? So I actually wanted to see what the alternatives are, right? If you spend more time configuring your Spark infrastructure, changing the Spark configuration, you can do that, right? You can spend a lot of time on it. Now, we all know time is money, right? It takes certain, whatever it is, finite amount of money for that spending amount, the extra amount of time. And it's same thing with buying more hardware. Buying more hardware, again, same thing. So like I said, I wanted to explore if there is a cost-effective way of doing this, right? So I wanted to explore different options using which I can get more out of my Spark infrastructure and get better throughput of Spark. But like I said, operate within certain budget limitations. That was my key deliverable there. Now I have some assumptions. What I did was, the way I went about is, based on my previous experience and also talking to customers and stuff, I looked at a standard Spark deployment. What is the kind of Spark infrastructure that people generally deploy, right? So I took a note of that infrastructure and I built a scaled down version of that same infrastructure in our lab, right? Because obviously I don't have a large number of nodes at my disposal. And when I did that, I also paid attention to what is the kind of infrastructure like CPU and memory capacities that people generally have in a standard enterprise Spark infrastructure. So I kind of took the same configurations and I repeated that. I created that, a scaled down version of that in our lab. So, but also I actually wanted to come up with a representative workload, with a workload that actually represents a good use case. Now, classification, clustering is a very good use case. It has its applications in fraud analytics, customer segmentation and stuff like that. So it's a very good use case, which is common in a lot of Spark deployments, Spark projects. So I said, okay, let me take a workload, which is a good representative of that kind of use case. And I went with Kmeans. And just a quick overview of the Kmeans here. It's the definition from Wikipedia. It's one of the oldest and most commonly used clustering algorithms. So basically what Kmeans does is it groups the given set of observations into clusters by determining what is the nearest mean for this observation, based on the nearest mean of the cluster, right? And it's an iterative process. It actually does it in repeative steps. In the first step, it actually it's an assignment step where it assigns the observations to the cluster, like I explained before. And then it recalculates the mean of the cluster and figure out what is the centroid for that cluster. So this process repeats until the algorithm has converged. Basically, that means there are no more changes. So it's an iterative process. So that's the Kmeans workload I took to go with my Spark configuration. Now here is my hardware and software configuration. I have a 4-node cluster. I have a management node and 3 data nodes. And the cluster is homogeneous in terms of CPU and memory. They're all the same. Where it differs is it has the management node has just boot drive for storage. There's no storage because I'm not going to be storing any data there. The data nodes have Intel DC-P4500 SSDs for storing the input data. And then I also have 2 Optane SSDs on each of the data nodes. And I actually use those, before I get there, but the software configuration, as you can see, I'm using Hortonworks Data Platform, and I'm using Spark version 2.2.0. Now, the Optane SSDs, the 2 Optane SSDs I have on each of the data nodes, I use it for 2 different purposes in 2 different test cases. One, I use it as a spill drive, because as you know, Spark, when it cannot fit the data set into memory, it starts shuffling to the disk, right? So in that case, I'm actually using the Optane SSD as the shuffle drive. And in the other test case, I'm actually using Optane SSD as a memory pool. Now you may be thinking that doesn't make any sense, right? Optane, I'm saying SSD, it's a block device. How can it be used as memory? So let me give you a brief introduction of what Optane is and what Intel memory derived technology is. So SSDs traditionally have been based on NAND technology. One of the features of NAND technology is that data is written in pages and erased in blocks. So you have SSDs have sectors, multiple sectors constitute pages, and multiple pages constitute blocks, right? But because of the way NAND technology works, like I said, it can only erase in blocks. So if the data has changed in some pages and needs to be rewritten, then the good data needs to be read and written to another location, and then the old block erased, and the data needs to be rewritten and stuff like that. So it may also include additional reads and writes if the new location is not empty, right? So this multiplying effect is called as write amplification, so because of which NAND-based SSDs are generally over-provisioned. This also means there's more work that the controller has to do, right? The SSD controller, such as determining the best block to write, such that all the cells in the die are evenly used over a period of time, right? Which is called wear leveling. And then this process happens in the background to make the whole write process as efficient as possible. This is also called as garbage collection. So all these phenomena are happening in the background in NAND-based SSDs. Optane technology, on the other hand, is a differentiated technology. It's bit addressable, and you can write in place. So because of that, the SSD is so responsive, especially in like a typical real-world mixed read-write kind of workload. And the SSD is so responsive that we actually call Optane as the world's most responsive SSD. And there is no write amplification or any of the other phenomena I explained before, because like I said, it's bit addressable and you can write in place. So an Optane SSD has a differentiated endurance. And in fact, the endurance capabilities of Optane is why it's actually enabled to be practically, practical to be used as a memory in the system. So that brings us to the next usage model of Optane SSD, right, which is software-defined memory. We have a software product called Intel Memory Drive Technology, and it's an intelligent software that exists at the virtualization layer below the OS. So when you install IMDT, it actually updates the BIOS tables and presents the combination of DRAM and SSD as a single large pool of memory to the OS. And take a moment to actually think about it, right? There is no change from the OS or the application perspective, right? Because by the time OS comes up, it doesn't see the block device anymore, because IMDT has taken over and it has presented to the OS as a single large pool of memory. And the way the application or the OS interacts with it is just the way they have always been interacting. So there is absolutely no change from the OS or the application level, or even the high-level programming interfaces, right? Behind the scenes, IMDT is actually leveraging Optane device. It actually uses DRAM as cache. So there is some amount of DRAM required even if you use Optane as memory, using Intel memory drive technology. So how much DRAM would you need depends upon how many Optane devices you want to use in your system for IMDT. So there are two different usage models, right, even in case of IMDT. So you can use it to expand the memory of a system beyond the limited DRAM capacity. So if you have a system, you're not limited to 3 terabytes or whatever it is memory that you can have in a system, right? You can expand the memory by however many PCIe-based Optane devices you can add in your system and run IMDT. Because Optane, like I said, it's at the end of the day, it's an SSD. It's a PCIe NVMe SSD. So you can have more SSD if you have more PCIe slots that you can use. You can have Optane devices, leverage IMDT, and you can go up to like 20 terabytes or even higher of amount of memory in your system. You're not limited by the 3 terabytes or whatever it is that you can have if you just use DRAM. Also, the other usage model is to replace DRAM, right? You can actually replace DRAM with IMDT. So now you have the same memory capacity as you would when you added DRAM, but now at a lower cost. So we all know DRAM is quite expensive. So what IMDT enables is a larger memory pool at a lower cost. That's the key there. So with similar performance as that of more expensive DRAM. Now that could be a very interesting proposition for a lot of Spark applications, right? Because a lot of Spark applications can certainly benefit from larger memory, right? And if that benefit comes at a relatively lower cost, it's a win-win with respect to total cost of ownership of your entire overall infrastructure. So I wanted to see how IMDT performs for the Kmeans workload, because that's what I took, right? My workload is Kmeans workload. So I'm going to walk you through my findings with an illustrative analysis of my test cases. I'll show you the CPU and memory utilizations for each of the test cases. In the top right corner of the screen, you see the CPU utilization chart, and in the bottom right corner, you see the memory utilization chart. So first up, I ran a baseline Kmeans workload, right? Meaning I don't have any IMDT on the cluster, and I chose a scale factor for the workload that fits entirely into the memory available in the system. So as I mentioned before, I have about 192 GB of DRAM. I showed you the configuration on each of the 3 data nodes. The sample that I took, the Kmeans sample that I took is a 1.2 billion samples, Kmeans workload. And as you can see on the screen, it took 5.3 minutes to run this workload. And the data set size is big enough to use almost all of the available memory, because that was the key. I was always monitoring if it's using the entire memory or not, right? So to start with, I actually chose a configuration of Spark, which is like kind of standard, right? So there are typical guidelines that a developer would follow to allocate resources to Spark applications, right? For example, keeping the cores per executor to 5 or lower, and assign number of executors based on the number of cores available on each of the nodes, and allocate the memory available equally among all the executors, right? Some of the standard guidelines that you would follow for any Spark application. So with that kind of standard configuration, I got a runtime of 5.3 minutes for that particular workload. Again, it fits entirely into memory. The next thing I want to do is I wanted to run the same exact workload. I wanted to add IMDT, but I just wanted to make sure that just by adding IMDT to the system, nothing changed. So as you can see in the memory utilization chart, now I have more memory available because I have 2 Optane SSDs with IMDT on each of the data nodes, right? So, but I'm not using any of that memory because, like I said, I took the same exact workload again just to make sure that nothing changed. And of course, it did nothing change. Now I have a larger memory pool, and the CPU usage is also more or less the same as before, as you can see in the previous chart compared to the next one. And the overall workload performance is, again, exactly the same, which is like 5.3 minutes to the dot, right? Now, as I mentioned before, I use typically standard guidelines, right, to configure Spark for my workload. Now, I could tweak a lot of parameters in Spark and Yarn to get a better performance for my application, right? That's a typical dilemma faced by a Spark developer. Is this the best I can get out of my system, or is there anything I can do, right? I mean, sure, you can spend a lot of time tweaking a lot of variables in your infrastructure to get the best out of it, but if the workload that you run is more or less the same, then it makes sense, right, to spend some time, fine-tune your Spark configuration and be done with it once and for all. But typically, that's not the case, especially in large enterprises expanding on their machine learning and AI analytics projects. If you have seen some of the keynotes, the kind of Spark applications that they are running with healthcare or finance, it's mind-boggling, right? The workloads are not static. They change all the time. And for somebody to actually spend a lot of time on each to configure your Spark configuration for every workload is a lot time-consuming process. So, like I said before, time is money, and you can spend a lot of time, which means that you're actually spending a lot of not just spending a lot of dollars, but also more time spent on your configuration or optimizing your configuration means more time to market, right? That's the key there. Now, before I go further, let me show you some configuration changes I did, right? I still want to show you what it took for me to change the configuration, to optimize the configuration, to get a better out of that same exact baseline, right? So I wanted to maximize my memory and CPU utilizations, right? Because obviously I want to put all the resources I have at my disposal to good use, right? But assigning memory to Spark executors wasn't straightforward. For instance, when I actually chose 10 executors and tried to equally distribute the memory to each executor, Spark actually reduced the number of executors assigned based on how much overall memory I actually allocated to Yarn, right? And because of that, memory was not completely utilized. So only 2 nodes had actually maximum memory allocated to the JVM heap, but the third node had almost 60 GB less memory allocated. So all in all, I had to play back and forth around quite a bit to determine the best configuration that still fully utilizes the resources, right? And once I know that the memory utilization was good, then I actually proceeded to increase the number of cores assigned to each executor. Now, since the Kmeans workload has some stages that are more CPU intensive, so those stages got accelerated. So, and now the overall performance actually improved. But I had to make sure that all the memory was still fully utilized to the maximum, so that the other stages that are more like memory intensive or memory bound don't slow down, right? And you can see I actually got a better performance out of the configuration, out of the tweaked configuration. Now the workload ran in 4.5 minutes. Now I tweaked the configuration even further. And in this case, I actually have less cores allocated to each executor. It may seem counterintuitive, but I actually got the best performance so far with this configuration. So the performance actually improved from 5.3 to 4.5 minutes earlier, and even further to 4.1 minutes now, right? So again, but each workload needs to be looked at closely and come up with that ideal configuration to get the best runtime possible. Now, either that, or you could straight away benefit from a larger memory pool, right? Because after all, Spark is known for in-memory processing capabilities, right? And the more memory you can throw at Spark, the better it could be, at least for most Spark applications. So the key I'm trying to highlight here is that you can spend a lot of time tweaking the configuration, and I have shown you that it is possible, in certain workloads to actually get a more better performance than than going with the standard configuration. Or if your workloads are varying so much, you can actually spend a little more, and just with your standard configuration and more memory, you can get better performance. So that I took the workload. Now this is my actual workload that I want to test with, right, for IMDT. So I increased the scale factor of the workload such that the data set doesn't fit into memory anymore, right? It's a bigger data set, and Spark starts shuffling to the disk now. And like I said, this is a test case where I actually used Optane SSDs as block device. And because the data set doesn't fit into memory, Spark is shuffling back and forth from the disk. And serialization, deserialization happens, And because of that, you can see the runtime I got is 43 minutes. It's a 2 billion sample. It's much larger workload, almost twice as large as or even more than the baseline workload, right? Now, so what I'm showing here is given the amount of DRAM, this is how long it would took, right? The CPUs, if you see the chart for the CPU utilization, they're not fully utilized, right? Although it's higher than the previous runs I've shown you. Now, I could repeat this exercise I had done with the previous workload, tweak the configuration, spend a lot of time trying to get a better performance from my infrastructure for this particular workload. Either that, or I can choose to actually run the workload, but I gave more memory resources available to me by using IMDT. And as you can see, it actually resulted in 3.5 times better performance compared to what it took just with the standard DRAM. Now, I did not run this workload by throwing more DRAM at it because obviously I don't have that amount of DRAM, terabytes of DRAM at my disposal. But I was trying to operate, like I said before, that's the key, right? I was trying to operate within certain budget. That was my goal. I wanted to operate within the budget and still get the better performance out of my Spark. So on that note, let's look at the cost perspective of what I've gathered so far. So I told you I've added 2 Optane SSDs per node, and I did a breakdown of the increase in cost compared to my baseline configuration. Note that all these numbers are actually based on real code from a third-party system provider called as Colfax International, and the dollar amounts are all real as of actually May 27th. It's just a little more than a week ago, right? So for an added cost, as you can see, pay close attention to the numbers there. For an added cost of 20%, so I added 20% cost to my overall infrastructure compared to what I had previously, the standard DRAM configuration, I get a performance improvement by a factor of 3.5 times. That's like 72% improvement in performance for 20% added cost, right? That's a big gain right there. Now, but if you see, the CPUs are still not highly utilized, right? I have 3 data nodes. I have, if you would have noticed my configuration, there were about 72 virtual cores on each of the nodes, but the CPUs are underutilized. So I wanted to attempt at another potential benefit. So I've already shown you in the previous case what the benefit IMDT gave me. With 20% added cost, it gave me 72% benefit. But now I saw that the CPUs have resources that I'm not utilizing. So this is another potential benefit, right? A reduced data center footprint. Now I decommissioned a data node altogether from the cluster and adjusted the number of executors accordingly. So as you can see now in the configuration I've listed, now I only have 2 data nodes. Now if you see the CPU utilization chart, the CPUs are almost choked, right? The CPUs are completely utilized. And the runtime was better than what we got with the baseline DRAM configuration that had more nodes. Remember, when I had 192 GB of DRAM with 3 data nodes, it ran for 43 minutes, right? And when I removed a data node, but obviously I have IMDT, more memory now, and I got a runtime which is still lower than that baseline. So while you can most likely get better performance by adding the equivalent amount of DRAM or by adding more nodes, the cost will be much higher compared to the cost of memory from IMDT. So I want to show you the cost analysis of even this particular scenario, right? So let's take a look at the cost analysis again with the updated results. Now, compared to the baseline configuration, let's remember, 20% added cost gave us a performance improvement by a factor of 3.5 times. That's almost 72%. Now, 20% reduced cost compared to the baseline, because I removed a data node altogether. 20% reduced cost gave us a performance improvement of 30%, as you can see. So cost is the biggest differentiating factor here. I just want to make sure that you get the point that I'm trying to make here. So this chart is just an alternative to show you how much it would actually cost you. It's just an informative slide to show you how much it would cost if you were to have the same amount of memory I got from IMDT by adding IMDT. If you want to get the same amount of memory but using all DRAM, right? The cost difference is about 36%. So when compared to the baseline configuration. So it's like I added 20% cost and I got 72% performance benefit. But if I add 40%, what is the cost per performance is what you want to see. So we are targeting the workloads that make sense, that you were willing to get that little bit of performance hit for the cost per performance. The total cost of ownership of your infrastructure is that's a key statement here of my presentation. So like what are the key takeaways, right? So as we saw in the test case, you can reduce the manual optimization simply by having more memory available at a reduced cost. For workloads that are not fully utilizing the CPUs, you can actually increase the CPU utilization, right? That's a key statement, that you can actually increase the CPU utilization and get better runtime by reducing the cluster node count in certain use cases, right? Which means that you can reinvest your dollars into a higher count processors. So that's, again, a big potential benefit there. So bottom line is tuning is difficult, right? Tuning your Spark configuration for every workload is difficult, and it has very little benefit, as we saw in the previous slide. Spill, again, shuffling to the disk is nowhere near the best. It's okay in a pinch, but if you have already fine-tuned your workloads, then it may be a better proposition. But like I said, if the workloads are changing all the time, it does not make any sense. Using IMDT is a very good alternative versus more DRAM. That's what I wanted to show you, and that's exactly the numbers that I've shown you. It works, right? So we all know workloads are big and variable. So it makes sense to build with IMDT for best total cost of ownership. And here are some online resources available for you if you want to learn more about Intel Optane technology or Intel memory drive technology. I actually also have a technical brief published. I have talked about my findings optimizing a Terasort benchmark. It's a micro benchmark using Intel memory drive technology. And that's the third link you see on the screen. That brings us to the end of my presentation. I hope this has been an informative session for you. A few minutes for questions, but you can also chat me up separately offline. Thank you, and have a great rest of the conference.
So you mentioned using IMDT in lieu of memory at times. So question for you, in case your app needs a lot more, if you undersize your memory for some reason and give more IMDT, would that impact performance? And what kind of performance degradation can you expect?
So, like I said, the way IMDT works is you still need some amount of DRAM. What it does is it actually does prefetching. So if you have a certain amount of DRAM, and how much DRAM, like I said before, how much DRAM you would need depends upon how many Optane devices you're going to be using for IMDT. So what it does actually is internally, let's say a simple example would be if you run a SQL query like select star from first name, comma, last name, right? And first name, last name are fixed data types, right? So let's say it's 200 KB of data. The way IMDT works is it actually does prefetching because it has, like I told you before, it's an intelligent software. It's a machine learning software, so it's trying to detect patterns. So the next time you run that routine, it actually gets the data from Optane SSD ahead of time and puts it into DRAM, prefetching. That's how it makes it better. So it just needs, and we have in the Intel Memory Drive Technology setup guide, we actually have recommended values for the amount of IMDT you want to get and what is the equal amount of DRAM that you would need for a best possible scenario. So we have that recommended settings in our setup guide.
Hi. So this IMDT disk is put in the same physical address space of the DRAM?
Correct. So it's not a separate form factor or anything. It's just an SSD. It's a software-defined memory. So the IMDT is actually updating the BIOS tables and presenting a large pool of memory. So from the OS or application perspective, there is no change. It is still a block device. Our hardware is still SSD, But IMDT has updated the BIOS tables, and the OS doesn't see the block device anymore.
Okay, so it will be like the internal implementation could be, let's say, if you are putting, let's say, 1 TB of IMDT in a disk, then it will have a 1 GB of RAM as a front end, and internally the software will do this whatever
Correct.
the LRU algorithm between your back and this
Yeah.
one and this RAM inside it. Okay.
Correct.
So from OS point of view, let's say if your first 1 TB is the RAM, and then you extended by 3 more TBs using IMDT to give a 4 TB of whole physical address space. The OS has no way to know that the memory address starting from after the first TB is belong to the disk. So it will start using all 4 TB assuming as a disk. So how are you going to manage it? So it's going to, without informing this to OS, it will lead to a lot of inefficient memory fetching, right?
No, so maybe we can take this offline in detail, but like I said, the software actually is at the virtualization layer. If you think about how virtualization works, it's similar to that, right? It has already updated the BIOS table. OS has it has no means to know that there is some address space that belongs to DRAM and there is an address space that's coming from the SSD. That is seamless for the OS because IMDT has. Correct. Correct.
Kmeans is a very nice sequential access pattern. It makes it very easy for your prefetch to work well. Actually, the OS file system would prefetch well for that case. So to me, it's more a knock on spot spill efficiency. It would be nice if you can try some workload that's a lot of pointer tracing. I'd like to see the number.
So I just want to quickly touch base, right? So you're correct. So there are 2 ways where the way IMDT works. The first case was I explained before, right, in which it does prefetching. Now, if the workload is very random in nature, that there is no way to identify patterns, there is still a way IMDT works very well. And the way it works well is if the workloads are highly parallelized. Because IMDT, it's not a simple software. It's very intelligent software. It actually works closely with the CPU. And what it can actually do is if you have highly parallelized tasks, it can actually tell the CPU that while I go and fetch the data for the previous task, continue to the next task. So it works closely with the CPU. Because in the end, in a parallelized workload, the overall performance of the workload is what matters. It doesn't matter how long it took for the individual task performance. So that's the key there. So IMDT can still benefit if the workload is highly parallel, even if it is random in nature.
Okay, and that's all the time we have for questions. I'm sure you can corral Ravi outside if you have more questions for him. Thank you.